Okay, see. Universal specification. So what do you mean by universal specification? See, suppose there is a statement P of X is something. P of X is some statement. Maybe X is pretty, X is good, something like that. P of X denotes something, right? For all X, P of X, I think you know. For all X, P of X means what? Everybody is pretty or everybody is good, right? So from for all X, P of X, one can conclude P of Y is true, where Y is a free variable. So can you understand why this can happen? Because P of X is true for all the values in the domain. So if that happens, then I can say that P of X is true for some X equal to Y, where that Y is coming from the same domain. Is it clear? Hello? Hello, are you all listening? Can you all hear me?
Ma'am, can you repeat, ma'am?
1 minute, 1 minute. Even I should, I think, increase the volume also. Okay. What I'm saying is, see, for all X, P of X. So what is for all X, P of X? Suppose if I say P of X denote X is good. What do you mean by for all X, P of X? Huh. Everybody in the domain, whatever domain we say, that domain is good, correct? Everybody is good, correct or not?
Yes, ma'am.
Yes, ma'am.
Sorry. So for all X, P of X, from this, can I conclude some P of Y is true? Where Y is a person in the domain, coming from this domain. Particularly, I'm saying all the students in this class have got distinction. I'm saying some X has got distinction. X, I don't want to mention any name, so I'm saying just saying X. Some person in the class has got distinction. Is that correct? Say, okay, all the students in the class have got distinction. I'm saying Manav has got distinction. Is it right? From that, concluding that Manav has got distinction, will that be correct? Yes, say something, yeah. Whenever a particular thing is true for all the people in the domain, it will be true for a particular person in the
Yes, ma'am.
domain also, right? So this is
Yes, ma'am.
called universal
Yes, ma'am.
specific. Yes, this is called universal
Also here
specification.
the X and Y should be related in some way, right?
X is, see, X is coming from domain, all values of domain. Y
Also
is
like if suppose X is a student,
arbitrary
then
value.
Y should be also a student, or it can be any free variable.
Free variable, but maybe, of course, it is coming from the same domain. Obvious, right? Okay. Then universal, existential specification. So I say there exists X P of X. From this, I can conclude P of Y. Okay. Here you have to have some condition. See, from there exists X P of X, one can conclude P of Y, provided Y is not free in any given premises. You are using Y, right? So I'm saying there exists X P of X. There exists somebody who is good in this particular class, right? I'm saying particularly some Ram is good. So this is possible. How can I say some particularly Ram is good? This is possible only when that Ram is not appearing as a free variable in any of the other given premises. If it is appearing as a free variable, then you are not supposed to use that particular. You are saying some maybe Y is not a particular thing. So whenever you are concluding P of Y is true from there exists X P of X, you should be very careful that this Y should not appear as a free variable in the other given premises. Then only it is true. Right? I should not use the same thing somewhere. That means you are pointing out to a particular person. Suppose there exists X P of X is true. I'm saying P of Y is true. Then that Y should not be a particular name. I should not use Ram. I should not use y is somebody. Somebody, for somebody, this is true. That's all I'm saying. Okay. So y should not be a free variable. If it is a free variable, then that means that you are going to point out somebody, which is not possible. While we are doing the proof, I think it will be very, you can understand very well. So before going into this, I'll go to existential generalization. Generalization is more tough here. What do you mean by existential generalization? I'm saying P of y is true. For some value of y, okay, P of y is true. Okay, then I can conclude there exists x P of x, right? I'm saying some y is good. Maybe that y is also coming from the class. So that statement can be rewritten as there exists x P of x, correct? There exists a student in this class who is very good. Why I'm not particularly saying, even you can here you can even say a particular person also. Ram is good, where Ram belongs to this particular class. Then I can say there exists a student in this class who is very good. That is applicable. But there that should not be there. You should not use a particular name. Simply you can say P of. So this is more tricky in the sense you have to be very careful. Don't read everything. I'll say. See, from P of y. See, P of y is true. Where y is arbitrary. I'm saying y is good. Y is good. P of y means y is good. Y is arbitrary value. You know what do you mean by arbitrary? Arbitrary means what? What do you mean by arbitrary? Randomly chosen. We are choosing the value randomly, right? So for random value y, if P of y is true, any value you are choosing, for that if P of y is true, then I can say for all the value of x, x is in the domain, P of x is true. This is possible only if y happens to be a randomly chosen value. So that's what here they have given some story. Okay, they have given provided that y is not free in any of the given premises. It should not appear as a free variable. You should not point out. I see. I cannot say instead of y, I cannot say Ram is good. Implies all students in the class are good. Is this correct? Will that be correct? So here I'm particularly saying some person. Ram is a free variable here, right? Free variable in the sense what? I'm particularly saying some person, Ram, from that particular class. That should not be there. I should use only a random value y. Right? So this Ram should not appear somewhere. Or I can say something like this. Some Ram is good in this class. That implies some Ram, I don't know who is that. Some Ram. If you take Ram or some what Vivek is good in this class. If you take any Ram or Vivek, he is good in this class. Then I can say for all x P of x, everybody is good in this class. Provided that Ram should not be a free variable. I should not use some other sentence before. I'm using Ram is a particular person. I'm saying Ram is very brilliant. That means there exists a person Ram. Particularly in this class, you are speaking about that person. So in that case, if Ram is good, you are not supposed to conclude everybody is good. Because you are particularly saying only Ram is good. So from that you cannot say for all x P of x. So suppose if you say some y is good, where y is an arbitrary value, then from that saying for all x P of x good is accepted. That's what mathematical theorems are proved, right? Arbitrary, from arbitrary value, if this is true, then it is true for everything. That way only many mathematical theorems are proved. If something is true for arbitrary value, then it is true for every value. That is universal generalization. Clear?
Excuse me, ma'am.
Yes.
Here, if y is fixed, let's say y is Ram,
No, I'm
so
not
then
fixing.
it becomes existent. No, Mr. Suppose we consider that y is fixed, so then it becomes existential, right?
Yes, yes. Suppose if you fix y, then I can say there exists x P of x. This is possible. But
Okay,
y should
got it.
not be fixed for universal generalization. Y should be what? A random value. Ram is good
Okay.
implies there exists x P of x is correct. Okay. Don't go much deep into this. When then and there, when it is needed, we'll use it. Okay, this we have seen. So what are all the three things we have seen so far? Universal, 1 minute, we'll write everything. Tell me what are all the things we have seen? Universal specification. What do you mean by universal specification? If something is true for every value of x, then it is true for a particular value. This is called universal specification. Existential specification. There exists x p of x implies p of y. Here there is a condition because here it is not true for everything. But I am writing some value here. So you have to take care that this y should not appear as a free variable in other premises. That is very much needed. That means you are specifying here something that is not possible, right? You have to be very careful. And then universal generalization. P of y is random, no? Then you can say for all x p of x. Here also you have to be very careful. These two things you have to be very careful. Then existential generalization, no problem. P of y is true now, then there exists x p of x. For some value it is true, right? Some Ram is good. So I can say there exists some person in this class who is good. That is not going to affect my statement, right? I'm saying Ram is good. Ram is good is same as saying that there exists a person in the class who is good. Both mean one and the same, right? That is not going to affect. Okay.
Ma'am, excuse me, ma'am.
Yes, ma, tell me.
Ma'am, can you explain the difference between the existential specification and existential generalization ones?
What is existential specification?
Uh,
I'm saying there exists a person in this class who is very good. So from that, I'm not supposed to conclude that some Vivek is good. Is that correct? No. I can say some Y is good. That is the only thing I can say. That's what Y is good I'm saying, but I don't know who is that Y. So that's why specifically I'm saying Y should not appear as a free variable in some other premises. That means you are pinpointing, right? You are pointing out somebody. If Y is appearing as a free variable, suppose some David is good, some Muhammad is good, somebody, if you are pinpointing, then that means that what? Y is appearing as a free variable, then that meaning is wrong because I'm saying only there exists x p of x. Somebody is good. That doesn't mean that Ram is good or David is good or somebody is good. I'm not supposed to say like that. So simply you say some Y is good. So you have to be very careful. Right? Okay. Then universal generalization. Existential generalization, it's quite easy. Yeah. Existential generalization, I'm pointing out somebody. Right? Muhammad is very good, I'm saying. That is a given statement. So from that, I can very well say that there exists a person in my class who is very good. That's possible, right? For that, you need not check any premise or anything, no condition, nothing is needed. So for these two things, no specification, nothing is needed. Directly you can go from here to here, from here to here, from here to here, directly you can go. But when you are looking into these two things, you have to be careful. Okay, so we'll do some problems. I think, hope you'll understand. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. Is a mortal and is mortal. Okay. What do you mean by mortal?
will die.
Will die, yeah. Okay. All men are mortal. How do you symbolize this statement? No universe of discourse. Universe of discourse is not given. You have to specify that. So in that case,
Ma'am, we assume the universal discourse as X is all men.
well, I'm not. I'm not saying. I'm not assuming universe of discourse.
Okay,
Without
ma'am,
that,
ma'am, for all X P of X, we can assume P of X is mortal.
Shall I write h of x as x is human? Man.
Okay, yes, ma'am. Yes, ma'am. Forgot that.
Man. M of x, x is mortal. S denotes Socrates, small s. Specific value, right? Okay.
Ma'am, for all x, h of x tends to m
What
of
does
x.
this mean? All men are mortal. How do you write? You said correctly, started correctly.
For all x,
Uh,
h of x
mm,
tends to m of x.
M of x. That means all men are mortal. For all x, whenever x is a man, then he is mortal. Okay, then Socrates is a man. How do you write that? H of x denotes x is a man. Socrates is a man. For Socrates, I have given a small thing. Yes, I am using
H of S.
H of s. So these two are given. What you are supposed to prove. Therefore, after that, whatever is there, that is the conclusion.
M of S.
M of S.
M of s. Okay. Shall we start doing proving this? Oh, here already it is there. See? Okay. See? I think with by seeing you can understand. These are the two given premises. This is the thing you have to conclude, right? So first I'm introducing this. For all x, h of x tends to m of x. So then you can go for what is this? From here to here, if you move, what is that called? Whenever x is a human or x is a man, then he is mortal. So can I conclude Socrates is mortal? Sorry, shall I conclude h of s tends to m of s? When Socrates is a man, then he is mortal. Correct? From this one is correct.
Yes, ma'am.
Why it is correct? Because I'm checking
Universal specification.
universal specification. Because I'm checking whether Socrates is a man. If Socrates is a man, then he is mortal. H of s tends to m of s. Okay, so this is one I have done, and then I'm taking this h of s, rule P. So combining these two things, what you should get? Combining these two. Second and third, if you combine, what will you get? P
M
tends
of
to P,
S.
comma P.
M of S.
M of
M
S.
of s. What is that called? In a rule, what is that rule called?
What
P,
is
P
ponens?
tends to. What is?
Ponens.
Opponent. So M of S is what is M of S? Socrates is mortal. Okay, clear? Hello, got
Yes,
it?
ma'am. Yes, ma'am.
Okay. Here also, I think directly we can see it's very easy only. If everyone is happy, then someone is happy. Okay. Using what? Here, what they are using is for all x, h of x. Here, I'm not using. I'm using universe of discourse to be what? All people. Okay, I'm assuming all are people. Whenever I take x, x is nothing but a person, a human being, right? So how do you write everyone is happy? So what is the thing I need to prove here? I am assuming everyone is happy, then I should prove someone is happy. Everyone is happy, how do you write? Suppose h of x denotes x is happy, and my universe of discourse contains all human, all people, right? Then how do you write everyone is happy?
For all x, h of x.
For all x, h of x. Okay. So for all x, h of x should imply what? Someone is happy. Someone means Again, you don't worry about x is a human only. Okay, then. For all x, h of x should imply someone is happy and there exists somebody, there exists an x such that x is happy. How do you write that? Oh, you're all sleeping. Very simple thing here.
There
For
exists x, h of x.
there exists x, h of x. Okay. So only one premise is given. From that I have to come to the conclusion. Very simple. See? First one I'm introducing for all s h of x. Right? Rule P. Then what should I do? What you can use? I need there exists x h of x from this. So what rule you can use? Nama, what rule you can use? I can say some h of a is true. Correct earlier. Is it right?
Yes, ma'am.
Some
Yes,
a is in the domain, right? Some a is happy from the domain. What is this called? From 1 to 2, you are doing something, right? What is that called? What rule you have used?
Specification.
Universal specification.
Universal
Specification.
specification of 1. Okay. So now you know that some a is happy in the domain. So shall I write there exists x h of x? There exists a person x in the domain such that x is happy. So from here to here, is this possible or not?
Yes, ma'am.
It's very easy. I told you universal specification and existential generalization are very easy. Okay, it's possible. There exists x h of x is possible. This is nothing but existential generalization of 2. That's what given already. Very simple. So everyone is happy, then someone is happy. I'm saying all students in the class have got distinction, then somebody have got distinction. True. So out of the 3 questions, which question we'll do first?
The first one, ma'am.
Second
Ma'am,
question.
can you just go to the previous slide for a minute?
Sure.
Thank you, ma'am.
These 3 questions now we are going to do. Take down the first question. For all x, p of x tends to q of x, and for all x, q of x tends to r of x, implies for all x, p of x tends to r of x. So some problems, right? First one, for all x, p of x tends to q of x, comma, for all x, q of x tends to r of x, implies for all x, p of x tends to r of x. This is the thing I need to prove. They have given and here, and means comma, right? Both are true. So you tell me how to proceed. Think about it, even for a minute or 2 minutes, you think and then.
So we convert the premises into like P of A tends to Q of A using universal
First we
specification.
need, you're right. First we need to introduce, right? First introduce. Which premise you will introduce? You have to introduce and then you have to use the rule. Which premise you will introduce?
The first one.
First one. So that is rule P. Then
The second premise,
first you.
or we can change it to P of A tends to Q of A using universal specification.
Universal specification of what? Universal specification, it's easy, right? Assuming A is a person or A is somebody or A is something in the domain, if it is true for all value of X, it is true for some particular value of A is also. Oh, correct. Then I'm introducing this next premise. Then again using same. Here also, shall we use the same A? Yes, it is allowed. Because Q of X tends to R of X is true for all value of X in the domain, right? Here all are coming same domain. X values are coming from the same domain. So Q of A tends to R of A, universal specification of 3. Okay, then can you combine 2 and 4?
Ma'am, by
Yes.
hypothetical syllogism, by combining 2 and 4, P of A tends to all of A.
Of A. So using hypothetical
Syllogism.
syllogism. Very good. Hypothetical syllogism on 2 and 4. Okay, then
using universal generalization on 5.
universal generalization, you have to be very careful. So you know very well this A value is already a random value only. I'm not going for a specific value here, right? It is random. I'm saying, see, for all X, P of X tends to Q of X. No, then for some A in the domain, P of A tends to Q of A. Random value only. So here also it is random. And moreover, according to their condition, this A is not appearing any free variable in the given premises. It's not free. So you can use it. Since it is random, for all X, P of X tends to R of X using universal generalization of. Okay, please look into this for a while. Yeah, I'll take class till maybe 11:50 or 12 o'clock. It's fine. Hello.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Feeling very sad. Okay, no problem. 12 o'clock till 12 o'clock to the maximum, not more than that. Even I'll get bored then. Okay. Shall we move on to the second question then? First question, if you are comfortable, we'll move on to the third.
Excuse me, ma'am.
Yes,
Could
ma'am.
you
Yes.
go to the previous question before this one? Yes, ma'am. So here, h of A. So here A is a random value or it is fixed one?
A random value.
Okay, so from random value we can conclude that there exists x h of x.
See, here it's up to us here. Since it is for all X h of X, even you can call that as a random value or a specific value, it is not going to affect there exists as h of X. Even if your A is random value, there exists X h of X will be true. Even if it is a specific value, then also there exists X h of X will be true. Correct?
Okay, yes, ma'am. Got it. Got it.
Got it. Second question, have you taken down? For all X h of X tends to M of X, there exists X h of X. Okay. Second question is, for all X, h of X tends to M of X, so then there exists X h of X tends to conclusion, there exists X M of X. Implies, actually implies.
Ma'am, we can first introduce the first premise.
First one, okay, ma'am.
Then, ma'am, we'll use your UG to get h of A tends to M of A.
Universal
Generally.
US,
Sorry,
US.
US, sorry.
US of 1. Okay, rule T. If you want, you can write that, no issue.
Then
T
we'll,
means something you are deriving. Okay. Then
we'll
You can
introduce
use
the
second premise.
we'll introduce the second premise.
and we'll use ES to get H of A.
H of A. So here is it possible that here also you can use S of A? No problem. So which one we should introduce first here? There is something wrong. Can you find which one should be introduced first?
And this third premise which you have written.
Third premise you should have used first. Because after fixing, see, you are saying there exists some H of X, right? So
Yes,
who's that we don't know. First we will fix that. He is that person. Then that can be used here also because here it is random.
understood.
We should change the order. That's what I wrote. So whenever there exists is there, please be very careful. You got it what I'm saying? Please think about, can you understand? One minute. So first we should introduce this one. Then H of A. Universal specification of 1. Then for all x, H of X tends to M of X. Will be. Then now you can use, since you have fixed some value, there exists a person. So I don't know. So there exists somebody, I'm saying some A, for some A it is true. That same A here also I can use. Because here it is true for everything, right? That everything and something will not match. First you fix that something and then come to everything. So H of A tends to M of A. Universal. Here it is existential specification. Here universal specification of 3. Now use 2 and 4.
Mod exponents 2 and 4.
Mod exponents. Using mod exponents in 2 and 4. Then existential generalization is very easy one. So I can write there exists X M of X. Using existential generalization of 5. Clear? Okay.
Yes,
Hello.
ma'am.
You write this question. We'll do the third question also. Question you can take down. For all x p of x or q of x implies for all x p of x or there exists x q of x. Hint they have given use indirect proof. Okay. Third one. For all x p of x or q of x implies for all x p of x or there exists x q of x. So using indirect method. Indirect method, what do? You remember?
We take the negation of the right
The
hand side.
conclusion, right?
The conclusion is.
Negating conclusion. Negating the conclusion. So you have to apply De Morgan's law, right? A union B, the whole dash. So that is equal to A dash intersection R will become and B dash. Now I think again not of for all will become
There exists X, not P of
not
X.
of. Good. And
For all X,
all X not of. Okay, so to prove this one you have to take, that is for all X P of X or Q of X. Along with that, these two you have to take as given premise and you have to arrive at a contradiction. Whenever you have and, you can separate it using comma also. That means this is also true, this is also true. I'll write this one. It should lead to a contradiction. It is equivalent to a contradiction. Or it is equivalent to false. That is the thing we want to prove. Okay. So which one you feel that has to be introduced first? You learned something from the second question. So please.
There exists X.
There exists. There exists.
There exists X, not P of X.
There exists X, not of P of X. Okay. So 1 minute. Sorry. The premise there exists X P of X. P of X, not of P of X, right? Not of P of X. So from this, shall I use some not of P of A? Existential specification of what? Then which one you have to use now? You can use either first one or second one, whichever you want you can use. Which one will you use? Shall I introduce third one? It is up to us. Then for all X not of Q of X. Okay, then. What happened? Tell me. For all X not of Q of X. Huh?
Not of Q of A.
Not of Q of A. Now it is possible because already you fix some variable from the domain. The same you can use here. What is this? Universal specification of 3. So I can say not of P of A, not of Q of A. So not of P of A and not of Q of A. That is not of P of A or Q of A. Correct? Is this possible? Clear? Hello? Hello?
Ma'am, can you explain this again?
Nothing I'm doing. From the beginning, should I explain?
Ma'am, just the step 5, 6.
That's what I'm taking these two together here. Not of P of A, not of Q of A. So this is also true. This is also true. I'm taking them together. Adding addition of 2 and 4. Clear?
Okay.
Then I'm using De Morgan's law. This is A dash intersection B dash. What is A dash intersection B dash? A union B the whole dash. That's what I'm writing here. So
Yes, ma'am. Understood.
Understood. Using De Morgan's law on phi. Okay, ma. Now yet you have one more premise that has to be introduced, right? What is that left over? For all x p of x q of x that you have to introduce. Rule P. Okay.
P of A or Q of A.
But here you have to be very careful. While you are doing this, already this A, I'll go back though. I'll go back and now explain. I think you will understand, better understand. Universal specification. Okay, nothing is there. Okay. Sorry. I got confused. Very sorry. Here you can use because it is true for all values, right? You can use. So can you see a contradiction somewhere now? Some contradiction.
6 and 8.
6 and 8. Okay. So P of A or Q of A and not of P of A or Q of A. A contradiction from 6 and 8. Hence proved. So that's the thing you need to prove, right? Hence proved. So why this contradiction has occurred? Because of negating the conclusion. That means you are saying that conclusion is not true. No, so then you are coming to the new conclusion. No, the conclusion is true. Okay, please look into this carefully. Okay, ma. Shall we proceed? Hello?
Ma'am, in the previous slide.
Okay, ma.
Okay. I'm here. It is the negation of the conclusion is we have an and sign here. So to prove
Comma
here
can
it
be,
should be. Can we introduce?
comma can be given.
Okay.
Comma. And means comma. That means these two are true. This is also true. This is also true. So these two can be added as an additional premise now. And you are supposed to come to a contradiction. Arrive at a contradiction. Okay, shall I proceed? Shall we move on to the next? No.
Yes, ma'am.
So more than one variable here. Just to see, very simple only, right? Two variables are here. So two variables mean two universe of discourse. Two domains will be there, right? For both the variables, you need two different domains. Okay, see here. Show that Not of P of A comma B follows logically from this statement and this statement. Okay, so you have any idea how to proceed with this? Very simple. Can you please think about it?
I'm here x, y, like means for all x and for all y.
First, we can introduce that. Shall we introduce that first? Tell me which one we can introduce. Shall we introduce this first? For all x. This means for all, yeah. Simply if you use this means for all x only, both one and the same. For all y, P of x comma y implies W of x comma y. Rule P. Please listen, you may not be knowing it. You can go for a specification, universal specification, either on x first or y first. So I'll go on x first. So that means I'll replace a by x by a now. Clear? Hello? Clear? So I'm removing that. Next, I'm going for a specification on y. So I'll write P of A comma B implies W of A comma B. Here also I should write universal specification on x. Here universal specification on y. Then introduce not of W of A comma B. Rule P. So if you use 3 and 4, what do you get?
Not of P, comma B.
Not of P of A comma B. That's the thing we want to prove. Very simple. So if in double variables, if more problems are needed, I don't think this much is enough for you. I'll discuss. If it is needed, I'll take more problems. Or this level is okay. Okay, if needed, I'll do it in the revision part. Friday I'll do. Friday we'll have revision. Tomorrow maybe half of the class, before half of the class, I'll complete the syllabus. And after that itself, I'll start revising. Okay, Vama, shall I? Is this okay?
So, ma'am, basically we'll have module 1 and module 2 for our CAT 1,
Complete, right? Yes, from module 3, maybe a little bit of module 3 will be there. Today I'm going to start. Now I'm going to start module 3 after this.
Oh, okay, ma'am.
Okay, shall I stop here? I'll go to module 3. Group theory. Module 3 is group theory. Okay. So I think many of you have completed applied linear algebra, right?
Yes, ma'am.
So in that for vector space, under addition, you have studied some 5 properties. Can you repeat those properties? Those properties are going to come here. This is the basis for linear algebra actually. Tell me what are those 5 properties? Closed under addition. Associative property. Then identity, additive identity. Then inverse.
Additive inverse.
All these properties are going to come here, right? So before going into this, I'll tell you what is a binary operation. What do you mean by a binary operation? Suppose S is a set. What do you mean by a binary operation? It is a mapping. Suppose it is a function from S cross S to S. That means I take 2 elements of the set x comma y. X comma y will come from x cross S, right? S and y are from S na. X comma y will come from x cross S. So if I take any x comma y, then it will be again going to some x star y or some f of x comma y. Binary operation. See, to be more specific, suppose I take two elements from Z, 3, 5. Okay. 1 minute. Yeah, I'm getting a call again and again. Just 1 minute. I'll come back. 2 minutes. Hello. I'm sorry. Okay. See, so then a binary operation star, for example, if I take 3, 5, okay, 3, 5 from Z, I'm taking a pair of elements I'm taking, then 3 plus 5 I'm performing. What is this plus called? Plus is called a binary operation. What do you mean by a binary operation? It operates on two operands. 3 and 5 are called operands, and plus is called a operator. So why it is called a binary operator or binary operation? Because it is operating on two elements, and 3 and 5 are called operands. Am I right? Can you understand? Hello? Hello? Are you all there?
Yes, ma'am.
Yes. So can you list out some of binary operations you know already? Addition, subtraction, multiplication, division, many things are there because all these operations need two elements, two operands to be operated. Clear? Hello?
Yes, yes.
Okay. Even matrix addition is also a binary operation. If you are adding two matrices, how do you add? You need at least two matrices, right? So it's a binary operation. Matrix multiplication also you need two matrices. So matrix multiplication is also a binary operation. Okay. So please listen now. Definition. I'm directly going to the definition. See, there is a set G with the binary operation star. I'm taking a set. Maybe you can consider a set of integers. I'm using, instead of star, I can use plus. Star is here general, any binary operation. If you want, you can go by specific, either addition, subtraction, or anything. Right? See, a set G. G is some set. Star is some binary operation defined on it. Then I can call G comma star together as a group if and only if all these four properties are satisfied. First one, closure. Whenever I consider two elements A and B in G, then A star B should be in G. G is a star is any binary operation. It may be plus, minus, or anything, right? Then associative. If you consider any three elements, I am always speaking any three elements from G, then associative property holds good. If star is replaced by plus, now what you should have? You should have A plus B plus C is equal to A plus B plus C. Clear? Then existence of identity. Identity, I think you know, right? Whenever, for all the values of A, you should be able to find an element E in such a way that A star E should be equal to E star A equal to A. Existence of inverse. For all A, you should find an element A dash such that A star A dash equal to A dash star A is equal to that identity. If all the four properties are satisfied, then that particular set along with the binary operation star is called a group. It's called a group, right? Please look into this definition once. Very carefully. Please look into this definition carefully. Shall I proceed? Okay, I'll take some example better. Okay, first question. What and all properties I told you? G is a set. Okay. Star is a binary operation. Star is a binary operation. G is a set. Star is a binary operation. Clear? First property, closure. Closure means what? For all A comma B in G, always A star B belongs to G. That star can be any binary operation. Second one, associative property. What is the associative property? For all A comma B comma C in G, A star B star C equal to A star B star C. This is called associative property. See, there is a specific term called semi-group. If these two properties are alone satisfied, then that G under the operation star is called semi-group. Two properties are satisfied, right, out of four. So it is called semi-group. Suppose along with this, identity also exists. What do you mean by identity? So for all A in G, suppose there exists E in G such that A star E equal to E star A equal to A. If this is also satisfied, so if all the three are satisfied, then it is called monoid. That particular G along with the binary operation star is called a monoid. Then fourth one, inverse. Inverse. Okay, tell me. Inverse means what? For every. For all A, I should not say. For every A. Both mean one and the same. Every A you should have an A dash. For each an A, you should have A dash. It's not common. A dash is not common. If you fix some A, for that you should have one inverse, right? Such that A star A dash, both ways it should be true. Both are equal to identity. So even if the fourth property is also satisfied, then it is a group. First two properties alone, semi-group. First three, then it is monoid. All the four, then it is called a group. Okay, I'll take some example now. See, for example, I take n under addition. What is n? Set of natural numbers. Okay, plus is addition. Okay, now tell me. What and all properties will be satisfied? Closure will be satisfied. If you consider any two natural numbers, will that be correct? Please tell me. Think and say.
Yes, ma'am.
Yes, ma'am. Hello. Closure will be satisfied if you add any two natural.
Yes,
will that result in a natural number?
yes, ma'am.
Okay, sorry. So for all A comma B in N, A plus B always belongs to N. Good. Then associative. Will it be associative? If you consider any three random natural numbers, you add in any way, it is going to be associative because addition is always associative. Operation is associative. If the operation is associative, if you add any three natural numbers in any order, it will be always true. Correct? Clear? Shall I proceed?
Yes, ma'am.
Okay, what will be the identity element under addition? What is the identity element here?
Zero.
Zero. Zero is there in natural numbers?
No, ma'am.
No. So, additive identity is zero. And it does not exist in N. So, therefore, 0 does not belong to N. So, N under addition is simply a semigroup, not more than that. Accept? Point clear? Hello?
Yes, ma'am, it's clear.
Clear. Okay. So, can you give an example for a monoid? Can you extend this? One more property can come. Can you give? Monoid. It should be a monoid.
Multiplication.
I'm asking you, can you give me an example for a monoid? Yes, ma. Just extend this and tell me, yeah, what is missing?
And for whole numbers.
Ah, very good. So W comma plus, if you consider, it is a monoid. for all A comma B in W, A plus B is always there in W. Any two whole numbers, if you add, it is again a whole number. Then associative property also hold good, because associative property, it is dependent, very much dependent only on the operation, right? So associative property holds good for W as addition is associative. Commutative, associative, all these things depends only on the operation, not on the set of numbers. Clear? Okay, va? Next. Identity. For every A in W, 0 belongs to W is the identity. So that A plus 0 is equal to 0 plus A is equal to A. Clear? Got it? Hello?
Yes, ma'am.
Yes, ma'am. So inverse will exist here. What could be the inverse? Inverse, if I go for every A in W, minus A is the inverse. But minus A does not belong to W, right? Will it be there? If 1 is there in W, minus 1 will be there in W? No. Clear? Hello? Are you all listening? I can understand over, I think, saturated. I will leave you with this example. Hello, bache. Okay, so therefore, W is not a group under addition, but it is a monoid. So can you extend this so that you can tell, find a group under addition? Just extend this, add something more on this and tell what will be the group then under addition.
Integers.
Integers, very good. Z under addition is a group. Set of all integers under addition is a group, very good. And even set of all rational numbers is also a group. Set of all real numbers is also a group. Set of all complex numbers under addition is also a group. Okay, I'll stop here. I'll upload the second module today. We'll meet tomorrow.